Alright. Hello, everybody. My name is Ricardo Zamora, and I'm a student that studies biophysics.
My name is Khoa Tran, and I study chemistry.
My name is Dr. Richard Lombardini, and I am a physics professor and the PI of this project. We are all at St. Mary's University in San Antonio, Texas.
Today, we will be presenting our project on capturing solar energy with quantum dots. And so our project goals for this project is we aim to synthesize non-toxic quantum dots for use as fluorophores in luminescent solar concentrators. We also aim to computationally model optical efficiency of synthesized quantum dots as a function of quantum dot concentration in the LSC. Lastly, we'd like to ask ourselves, can efficiency be improved using a specific mixture of different sized quantum dots due to force through resonance energy transfer, or FRET? So another part of our project is we like to address supporting people and planet and prosperity. And how we do this is we look at 3 pillars of sustainability: environmental, economic, and social. First, for our environmental pillar sustainability, we want to find more efficient means to use solar power, which will result in healthier natural habitats and ecosystems. In addition, we like to reduce fossil fuel emissions, which will reduce ground level ozone and particulate matter, which both directly affect urban health. Second, within the economic pillar sustainability, new LSC designs could lead to formation of startups, providing jobs to the community. In addition, a higher LSC efficiency will wean us away from fossil fuels. Lastly, for the social pillar sustainability, we want to reduce harmful emissions, which can lead to improved health among disadvantaged communities. Secondly, we also want to offer interdisciplinary research opportunities through this project to minority undergraduate students as a crucial component of their STEM education. Lastly, LSCs can be used as windows on buildings, which can create sustainable living in urban areas with many high-rises.
We were able to synthesize copper indium sulfide quantum dots using a simple and established method. Different sizes of the dots were obtained by varying the time of nucleation, where larger size dots correspond to redshifted emission spectra. Based on the experimental spectra and using the Monte Carlo simulation, we were able to determine the percent solar average optical efficiency of the quantum dots as a function of concentration in an LSC of dimensions 12 by 4 by 0.8 centimeter, where 2 largest faces are open, 1 face has a photovoltaic cell, and the remaining 3 faces have mirrors facing internally. Here's the diagram showing possible pathways solar photons might take once they enter the LSC. The photons will exit the LSC if they are reflected off the surface, transmitted through the open surface, or are not emitted due to low quantum yield. Otherwise, they will be absorbed by the solar cell. Here are the spectra of our dots, and as you can see from the top left figure, larger size dots have higher absorptions. From the emission spectra, we can see that as we increase the nucleation time from 1 to 25 minutes, the emission spectrum redshift from 630 to 830 nanometer. The bottom figure are plots of solar average optical efficiency as a function of quantum dot concentration of 6 different sizes of quantum dots. And here's a table highlighting the data from the figure that we just looked at. And it is worth noting that the 20-minute nucleation time quantum dots almost reached 10% efficiency.
So, in conclusion, we were able to successfully synthesize different sized quantum dots. In addition, we're also able to calculate the solar optical efficiency as a function of quantum dot concentration in the LSC. But for our future work, we want to be able to simulate a mixture of different sized quantum dots that will allow an additional mechanism of energy transfer, otherwise known as FRET. And by modeling this different energy transfer, we hope to lower the amount of photons lost within the LSC in the Monte Carlo simulation and therefore increase the optical efficiency.